right, dude. We are live. What's up, guys? This is Dem Keys, and holy shit, we are on a bit of a streak. It seems kind of silly to be proud of this, but I'm proud of it. Uh, we are now doing our, I think, fourth talking stream. Um, how do I say this? We have been streaming. We have been doing talking streams for 4 days straight now. And I'm happy about that, dude. I'm pretty excited about that. And we are also making progress. Cutane, hello, hello. Welcome to the stream. How's it going? Um, Today we are doing more PyTorch studies. And yeah, I was just saying that I'm happy that the progress that I'm making is in deep learning. And hopefully I'm going to be able to take this soon into, you know, or how do I say this? Hopefully I'm going to be able to use this knowledge soon to solve my problems that I was having with TTS and speech to text and a bunch of those other things. I'm gonna be starting with TTS. Before that, I do want to get the basics down. And yeah. So yesterday, after yesterday's stream, I was expecting to finish reading what this. I was expecting to finish reading up on the training thing, but then I didn't do that. I ended up getting distracted with torch.compile, and I started doing a bunch of research on that as well, because that's supposed to be the next thing that I do after this. Like once we've learned how to train the model, and we all obviously know how to build the model and how to save the model. Once we've learned how to train the model, then I want to go over to torch.compile, because dude, there's quite a bit to explore there. And torch.compile, it does actually help in terms of speed ups. It does help, at least in terms of inference. I'm sure there's benefits on the training side as well. That's something for me to test out. But I had a bunch of different doubts about how things work, and how torch.compile gives you how it gives you speed ups. Because like I I understood that yes, torch.compile, it does generate fast code for you. It generates optimized code that can be used in place of the code that you have written. And it generates optimized code, or rather, it generates fast code that's optimized for whatever platform you're trying to run it on, be it a CPU, be it an NVIDIA GPU, or an Intel GPU, or whatever other platform. I understood that bit, but I needed to dive deeper into it to understand exactly how this new generated code is being used, where it gets saved, and how it gets saved, and how exactly does it get incorporated into the code without me even doing anything. And dude, yo, it's it's pretty amazing. It's great. Um, it's great the way that they've set all of this stuff up. So you, as the Python programmer, you don't need to worry about a lot of the low level stuff. You don't even need to worry about like offloading it to the GPU. As in you don't need to worry about writing the code for offloading it to the GPU. A bunch of that code just gets generated for you. You just need to specify that, hey, I want to do it for this device. And then, of course, when you have your input tensors and stuff like that, you have to specify that it's for so and so device. That's like a little bit of that's about as much effort that you have to put into it in terms of offloading something to the GPU, which, dude, that's a huge, huge convenience. That's a huge plus because that makes it so you as the Python programmer, you as the deep learning programmer, you just need to focus on building your models and um, what else? Well, building and training your models and even using your models. You don't necessarily always need to worry about the low level stuff because a lot of that gets handled for you. So yeah, I was reading up on torch.compile yesterday. I was doing a bunch of research. I had a conversation with Gemini about how these things work. Dude, at this point, asking Gemini is a lot better than doing a Google search because I can ask more um, I can ask more nuanced questions because I can ask it in like, regular language as opposed to having to use specific search terms like you would have to do in a Google search bar. I'm just able to ask regular questions and then ask follow-up questions to the answers that are given to those questions, and I can still get decent answers that way. And that's actually how I've been doing my research on torch.compile. So yeah, that's kind of why I didn't look into this training this training documentation yesterday. So today we're going to be doing that. Hopefully we are able to finish this today, and then after further from this point, I should be ready to just build models and, well, I mean, at least feed forward neural networks. I should be ready to just build um sorry, I lost my train of thought. Yeah, I should be ready to move forward in terms of learning different neural network architectures, because for the time being I wanted to get my basics down. I wanted to learn how to build a basic model, how to use the tools provided to build a model at all. Like, doesn't matter what kind of model, but a feed forward neural network is like the simplest model that you can, or the simplest kind of neural network that you can build. So that's a good starting point. I wanted to learn how to build a model. I wanted to learn how to train one, and also how to save and load the model's weights. And I also wanted to learn how to load data sets, load and use data sets. And throughout this journey, I've also learned that we have other libraries like Hugging Face Transformers and Hugging Face Tim that can be used to how do I say this? That I can use if I need extra components, extra things, extra utilities or functions or stuff that's not provided out of the box with PyTorch. I have access to uh, Hugging Face Transformers and also the Tim library, and I can use all of those components to build the model. Um, where was I going with this? Yeah, I think I was saying that I before moving forward with learning more complex architectures like convolutional neural networks or the transformer architecture and stuff like that, I wanted to get my basics down, and these are the basics. Also, torch.compile. At this point, I'm counting torch.compile as also a sort of prerequisite that I would like to know before moving towards more complex architectures. Because, um, dude, torch.compile is it's great because it can like speed up things for you. Um, no matter what your architecture is, you can always compile it to a faster version, and that's kind of cool to me because like you don't have to put a whole lot of effort in order to get that bit of speed up. I do need to look into um different ways that you could run inference on PyTorch models. Like, for example, how would I go about using something like TensorRT to run inference on a PyTorch model? And how would how should I say this? I need to find out if there are other ways to use a PyTorch model to run inference on a PyTorch model other than just doing it from within, from within PyTorch. Because currently I'm just using PyTorch, right? I build the model using PyTorch within my Python code, and then of course train the model, and then later on I can use the model with these trained weights. But I want to know if there are other, and I'm pretty sure there are. I'm saying I want to know if, but I know I'm pretty sure there are other ways to run inference on the model, other ways that tend to be faster in some cases than just running it through PyTorch. So I want to explore that as well, but that's going to be more of an advanced topic. I'm not gonna touch that right now. For the time being, I just want to get my basics down. Now, before we look into this, I want to go into this as well. I don't think we're going to go all the way to the end of this because this also goes into like this optional reading tensor gradients and so on. So I don't think I'm going to be reading this bit. I can come back to this later on. For the time being, I want to just kind of go over this thing, and this is going to cover what autograd is and how this system is used to perform backpropagation, which helps train the neural network. uh right, okay. So where was I? Give me a second. Let me hydrate, and then I'll start reading. Real quick, I just need to make a note somewhere so I remember this. Um, where is it? Here. Right. So, to do, finish reading up on Git branching and learn how to set up. Actually, I can make that. Yeah, okay, never mind. And learn how to set up a remote Git server without SSH. I've read up on this, and there is a way to actually there's multiple ways to set this up. I just keep getting interrupted, or I keep getting distracted. Saying I keep getting interrupted is it sounds like somebody or something is interrupting me, but it's me. I'm interrupting myself because I keep getting distracted, and then I don't finish that. And I need to learn how to set up the remote Git server thing because I want to do that. I want to get that done before I continue working on my VTubing app because I've set up a Git repo for it, and now I want to set up where exactly the remote for that repo is going to be, or where the remote repo for that is going to be. I'm not sure how to say that, but I need to set up the remote location for it because the remote location is going to be on a different machine. It's not going to be on the same machine that I'm currently streaming from. Actually, no, I think I said that the wrong way. No, the remote is going to be on the machine that I'm currently streaming from, but I'm not going to be working on the project on this machine. I'm gonna move it over to my Linux machine, So basically, I'll clone the repo on my Linux machine, which is why I want to set up the remote here. I want to set up the origin on this machine, but then I'm going to clone it on my Linux machine and continue working on the project there. So then, anytime I have updates, I can push them uh, to the master branch, basically. Actually, well, I mean, they're both gonna have a master branch technically, right? But yeah, I can push it to the remote repo. I just need to read up on all of that and learn how to set that up. Right. So let's carry on reading this, or let's start reading this because we haven't started reading it yet. Okay. Automatic differentiation with torch.autograd. When training neural networks, the most frequently used algorithm is backpropagation. In this algorithm, parameters, which is model weights, are adjusted according to the gradient of the loss function with respect to the given parameter. To compute those gradients, PyTorch has a built-in differentiation engine called torch.autograd. It supports automatic computation of gradient for any computational graph. Consider the simplest one-layer neural network with input x, parameters w and b, and some loss function. It can be defined in PyTorch in the following manner. Okay, so that's our input. Y is the expected output. Okay, then we have the weights and the bias. And wait, did I just click on this? Wait, if I click on this, where does this? Oh, this goes to tensor. Okay. And then Z. What is Z supposed to be? Oh, Z is supposed to represent the linear transformation, I think, because it says matmul X and Y. So that's a matrix multiplication between the input and the weight matrix, and then you add the bias to that. So that's your basic linear transformation. And then we have the loss function. Loss functions are interesting. I remember back when I first started looking into this, I did dive a little bit into loss functions, but then I kind of like moved away from it because, well, I had other stuff to look into, but I also kind of got lost with with details of different loss functions and how they affect the outcome, or how they affect, in this case, the training process, because the loss function's value is what's then used to compute the gradient and stuff like that. Okay. Um, right. So tensors, functions, and computational graph. This code defines the following computational graph. We have the input, which is multiplied by the weight, or weights. I think it's one. Okay. Anyways, we have the input, which is multiplied by the weights, and then that gets added to, or well, um, the bias gets added to the result, and then that whole thing is represented by this and this. So okay, this is just supposed to represent our linear transformation then, right? Oh, they're showing that this is what the computational graph looks like. Okay. So then this is supposed, Z is supposed to be, it's supposed to represent our linear transformation. And then we have cross entropy, which is our loss function. Y, I'm guessing, is the expected output. Yeah. Y is the expected output. And then based on, oh, Z is supposed to be our result. Z is not supposed to, well, okay, so yeah, technically I'm not wrong. Z is supposed to represent the linear transformation, but Z is actually the result. Z is the result of the linear transformation. And that is our, so Y is our expected result, and Z is our actual result. And then we pass both of these into cross entropy. We pass both of these into our loss function to calculate the loss. Okay, great. In this network, W and B are parameters which we need to optimize. Yep, okay. The weights and bias. Thus, we need to be able to compute the, give me a second. Thus, we need to be able to compute the gradients of loss. What? We need to be able to compute the gradients of loss function with respect to those variables. In order to do that, we set the requires grad property of those tensors. You can set the value of requires grad when creating a tensor or later by using x dot requires grad 2. 2? True. True method. Okay. True method? What? By using the x dot requires grad method. Okay, fine. A function that we apply to tensors to construct a computational graph is in fact an object of class function. A function that we apply to tensors to construct computational graph is in fact an object of class function. Okay, all right. This object knows how to compute the function in the forward direction. Oh, class function. Wait, function or functional? I think functional. Well, no, functional is basically functional contains methods which. So okay, functional is nn dot functional, and nn dot functional contains the functions that nn contains, but they are not. I guess the right way to say is that they're not differentiable, in the sense they're not tracked by autograd. So you can, like, if you're just looking to use those functions without doing back propagation and all of that stuff, then you can use the functional version of whatever. So in this case, like, um, I said whatever, I should also give an example, right? So in this case, let's say linear. Linear has an nn dot linear, but then you also have nn dot functional dot linear. So there is a functional version of that, and there's functional versions for a bunch of the different functions. Okay, this object knows how to compute the function in the forward direction and also how to compute its derivative during the backward propagation step. A reference to the backward propagation function is stored in the grad fn property of a tensor. A reference to the backward propagation function is stored. Okay, all right. Give me a second. Okay, sorry about that. So you can find more information about function in the documentation. Let's open that up and see what is here. Automatic differentiation with, wait, hold on. Oh, okay. All right. So we were down here. Base class to create custom autograd function. To create a custom autograd function, to create a custom autograd dot function. Okay. Subclass this class to implement the forward and backward static. Oh, okay. So if you want to create your own function um, that can be tracked by autograd, or that can be affected by autograd, you can then use this. Okay. So we are not going to be doing this. Um, at least while learning the basics, we're not going to be doing this. This is more of an advanced use case. Okay, carrying on. Gradient function for so and so. Okay, gradient function for so and so. Okay, cool. Computing gradients. To optimize weights of parameters in the neural network, we need to compute the derivatives of our loss function with respect to parameters. We need to compute the derivatives of our loss function with respect to parameters, namely, we need, oh, so this is how you get the derivative of the loss function with respect to weights and with respect to biases. Okay. Under some fixed values of x and y. Okay. All right. Yeah. Oh, hold on. That's interesting. Um, so the expected output does get taken into account as well. And of course, so does the input. To compute those derivatives, we call loss.backward and then retrieve the values from w.grad and b.grad. Okay, we can only obtain the grad properties for the leaf nodes of the computational graph, which have requires grad property set to true. For all other nodes in our graph, gradients will not be available. I didn't get that. For the leaf nodes of the computational graph, for all other nodes in our graph, gradients will not be available. We can only perform gradient calculations. Wait, if they say leaf nodes, does that mean like the end? And if that means the end, um, oh, is that why we do why we use the chain rule to do backpropagation? Because we can't calculate the gradient for the other stuff, at least through this. Is that where the chain rule comes in? So like we start from the end and then we kind of like go backwards, going through all of the previous nodes all the way to the beginning. Okay, for all other nodes in our graph, gradients will not be available. Okay, we can only perform gradient calculations using backward once on a given graph for performance reasons. If we need to do several backward calls on the same graph, we need to pass retain graph true to the backward call. Disable gradient tracking. Okay, by default, all tensors with requires grad true are tracking their computational history and support gradient computation. However, there are some cases when we do not need to do that. For example, when we have trained the model and just want to apply it to some input data, i.e., we only want to do forward computations through the network. We can stop tracking computations by surrounding our computation code with the torch.nograd block. Okay. Another way to achieve the same result is to use the detach method on the tensor. Okay. There are reasons you might want to disable gradient tracking to mark some parameters in your neural network as frozen. Okay. All right. Or to speed up computations when you are only doing forward pass, because computations on tensors that do not track gradients would be more efficient. Right, so this first thing here, the thing with like frozen parameters, I believe this is what gets used in fine tuning. Because like in fine tuning, you're training like certain parts of the neural network, and certain other parts are frozen. The parts that you're not planning on affecting or training or whatever, you freeze those parts. Okay, more on computational graphs. Conceptually, AutoGrad keeps a record of data and all executed operations along with the resulting new tensors in a directed acyclic graph consisting of function objects. In this DAG, leaves are the input tensors, roots are the output tensors. Oh, the output tensors are okay. So when they were talking about leaf nodes here, see when they mentioned leaf nodes, I was connecting that to like the output, and I was considering that to be the leaf. but apparently that's not true. Roots are the output tensors. By tracing this graph from roots to leaves, you can automatically compute the gradients using the chain rule. Okay, in the forward pass, AutoGrad does two things simultaneously. It runs the requested operation to compute a resulting tensor, and it maintains the operation's gradient function in the DAG. The backward pass kicks off when backward is called on the DAG root. AutoGrad then computes the gradients for each grad function. Okay, I'm gonna need to have a conversation with Gemini about this to understand exactly what's going on here, because I feel like I need to dive deeper into this just to get a high level, like, conceptual understanding. Like, I want to dive deeper into it, but not dive deeper into the math of it. I want to dive deeper into the into the concept, into I want to understand how this works conceptually without having to go into the math side of it. Okay, so AutoGrad then computes the gradients for from each gradient function, accumulates them in the respective tensor's grad attribute, and using the chain rule, it propagates all the way to the leaf tensors. Okay, DAGs are dynamic in PyTorch. An important thing to note is that the graph is recreated from scratch after each backward call. No, the graph is recreated from scratch. Um, After each backward call, AutoGrad starts populating a new graph. This is oh shit, I missed the ad timer. Okay, so there's an ad playing right now, so I'll see you guys in 30 seconds. I'll take a little hydration break. Give me a second. I'm just doing something here. Okay, all right. Welcome back from the ads. So, AutoGrad starts populating a new graph. Okay, this is exactly what allows you to use control flow statements in your model. You can change the shape, size, and operations at every iteration if needed. Okay, all right. Yeah. So I'm gonna need to do some deeper research into understanding what exactly happens during backpropagation, but I'm gonna need to do this without diving into the calculus part of it. I need to just get like a high level understanding, a conceptual overview of what is going on. That being said, for now, I guess we can just say that, yeah, um, for the time being, what we could say is that the model so the model starts with like random weights, right? I mean, it's not exactly random. There's um, even the initial random quote unquote weights. There's a certain, how do I say this? Because I'd seen this in the MIT lecture. They had mentioned that there's a way of picking good random weights, good starting weights. It doesn't have to be truly random, and that can kind of make your training process a little easier because you're not going to be like so far away from your expected result. But okay, for the time being, we can say that yes, the neural network is instantiated with random weights. It starts out with random weights. We give it some input, and then we get the output, right? And then we compare, we pass in the actual output and the expected output into the loss function to calculate our loss with respect to the weights, the current parameters, the weights and biases, and Also the input and expected output. I'm guessing those get taken into account as well. So after that, we have the loss calculated, and after our loss has been calculated, AutoGrad calculates the gradient, and based on the gradient, it optimizes our weights and biases or whatever the parameters might be. And then we just repeat this step over and over again until our loss has reached to an acceptable amount or the model is performing in an acceptable way. For the time being, I guess we can just say that. And I'm going to dive deeper into the backpropagation portion of it. Wait, did I say that right? That Yeah, yeah, yeah. Pretty sure it's AutoGrad that's calculating the gradient, and you have to give it the loss before. Well, okay, it's calculating the gradient of the loss function. I think that's an important thing to remember, right? It's calculating the gradient of the loss function with respect to the parameters, and then based on that gradient, we then change the weights and the biases, and then just run that back. Okay, all right. So moving on, optimizing model parameters. Now that we have a model and data, it's time to train. Wait, it's time to train, validate, and test. Okay, it doesn't stop at train. It's time to train, validate, and test our model by optimizing its parameters on our data. Training a model is an iterative process. In each iteration, the model makes a guess about the output, calculates the error in its guess, which is our loss, then collects the derivatives of the error with respect to its parameters, as we saw in the previous section, and then optimizes these parameters using gradient descent. For a more detailed walkthrough of this process, check out this video on backpropagation from 3 Blue, 1 Brown. Okay. So we need our prerequisite code here. I need to write this down because all of the other code that I have is for simpler stuff. Let me just copy this. Let me just copy this. Yeah, let me just copy this. So I'm gonna run this thing here. And then I'm gonna create, wait, oh, hold up, hold up, hold up. Yeah, let's clear this out. Yesterday I was looking into this, by the way, is the this is an example of the optimized code that gets generated by torch.compile. And there's like a bunch of different, you know, pieces here and there. It's not just one file, as I found out later on. Let's clear out this cell output, and then we need to create a new code cell and then paste this. Great. Awesome. So we don't need these. I don't think we need them. I think I already have data loader and data sets, and let me just, okay, let's go up here and confirm. Yeah, data set, data loader, everything is there already. Great. All right, let's just go over this code once more. So we have our training data. This is our data set. Well, this is our training data set. Actually, hold on. Root data, okay, train true. So this is kind of interesting. So if we set train to true, it's going to give us the training portion of the data set. like whatever is meant for training purposes. But if we set it to false, then it's going to give us the testing portion of the data set. I'm wondering if they have like, if they've actually separated them, or if it's just all jumbled up and each time it's giving us, I don't think it's jumbled up. I think they have separate training and test data sets that are part of this same data set. And then depending on, whether you say train equals true or train equals false, it'll decide which chunk of the data set it's supposed to give you. And then, of course, we need the data loaders, which are going to give us the functionality for actually loading the data. I need to kind of refresh my knowledge on the data loader as well, because I remember something about there being an iterator where you're able to iterate over whatever is provided by the data loader. So the data loader itself can be used as an iterator. Um, I think that's what it was. I don't remember. Hold on. We can give me a second. We can go back to the. I think it was here. Yeah. So here we have the data set. Okay. Okay. All right. Cool. Creating a custom data set. Okay. Iterate through the data loader. So this is our data loader, and oh, okay, all right, yeah. So the data loader is, well, I mean, okay, the data loader, I don't know. So because we are having to wrap it uh into this iter call to make it an iterable, so that we can then call next on it. So I don't know if out of the box it's actually an iterator or not. We can look into that. I don't remember yet. You know what? Okay, let's break this up into chunks. This is going to be our neural network. This is our basic feed forward neural network, which uh, first flattens the data. If, well, I mean, the flattening is done in the forward function. So it first flattens the data, and then that data is passed through our linear ReLU stack, which has just a couple of linear layers and a couple of ReLU functions as well. And then finally, we return the logits. And I believe the logits are passed through a softmax function at the end. Not, yeah, yeah, at the end. That's outside of the network. Okay, so let's copy this, create a new thing here. Actually, hold on. I kind of want this to be below the class definition. Oh, actually, I could have just, oh God, what did I just do? I just, yeah, I I messed up. So here's what we're going to do. Okay. We are going to copy this again because through a bunch of different undo operations, first I did undo on the cell, and then I did undo on the text that was inside another cell. And so one cell disappeared and then it just became a mess. Can I hold on? Is there any way for me to like, is there like a redo? How do you do redo here? So we have redo, redo again, redo again, not working. Okay. Somewhere in between, I did like an overwrite or something. Right. So this is definitely something I need to be careful of, because that mistake that I made, like, okay, here's the mistake that I made, right? I did this and then I did this here and then I did undo and there. That's That's what I did. And that is, holy shit, that is dangerous, dude. Like, how do I even. Okay, what if I paste the cell? There's nothing to paste. Okay. What if I undo? Nope. What if I redo? Okay. What if I redo again? Yeah, no. There is, like, this becomes a mess. I need to be, holy shit. I need to be so careful with this, dude. Like, this could very easily happen to my own code. Like, imagine you've written a bunch of stuff and then you accidentally did an holy shit, dude. Right, so we bring this here, and then we create this cell and then drop that here. And what I wanted to do here before I made that huge mess was all I needed to do was move the cell down, and I forgot that these things have that option to move the cell down. Okay, so we run that, and now we run this, which is probably going to download the data set. Is it done? I think it's done. Okay, right. So it's done downloading the data set, and now um, let me just print out the type of. So just so that we can go over this again, we've already gone over the datasets thing. It downloads the relevant dataset or loads the relevant dataset if it's already cached, and then it applies this to tensor transform to it. So we'll get the dataset in the form of a tensor. And then we use a data loader to load this in batches of 64. So let's try printing out the type for train data loader. It should just say data loader, right? All right. So then we have, what was it supposed to be? Label and image, I think. Feature and labels. Features and labels. Okay. Train features, train labels equals next iter train data loader. So what I'm guessing is going to happen here is that in train data loader, there's something that's keeping track of um, that's keeping track of some kind of counter. So each time you call next, it's going to give you like the next thing all the way until the end. So if I call next again and again, um, each time it should give me different information. So, all right, let's try printing out labels. So if my guess is correct, because we have a train data loader up here and we haven't run this again yet. So if I run this again, if I run this code cell now again, not the train data loader definition part, if I run this thing again, it should run next. It should call next on the train data loader. So we should be seeing a different set of data the next time that I run this. So let's, no. Okay. Yeah, no. I was wrong about that. So then how is it working? No, dude, that's how these iterators work, right? They have like something that's keeping track of some kind of index or something, and then that's how you're able to get the next thing when you call next each time. How is this? What am I missing? So each time that I run this, we have train data loader. Well, if I called it again, then we would probably get different data. But I'm wondering why. Um, oh, hold up. It doesn't change. It doesn't seem to be changing. Why is that? So is next just not being called? Wait, I'm confused about this. That's how this is supposed to work, right? Because like, okay, let's try creating our own like iterable over here. So let's say a equals, let's do 10. X for x in range 10. Okay. Then b equals next iter a. So a is a list, so it's already iterable, but like we'll wrap it into the iter thing and then call next. Okay. Uh, what if we run? Oh, wait. So if we create an iterator out of, oh, okay, I think I understood what the issue is. What we needed to do was create the iterator here. So let's say td iterator equals this. I think the issue is that we are creating an iterator each time. If we were not creating an iterator each time, so then I guess I should place it here and run that. Right. And then if we pass in td iter here and then print this out, yeah, there it is. Yeah, it's because each time it was creating an iterator, so I think each time it was just resetting the thing and then calling next on it. But now it's just creating the iterator once and then it's calling next again and again. So each time we have different data being printed. Okay, all right. Now, okay, all right. So to iterate over this, wait. So we have the train data loader, right? Is this the only way to iterate over it, or is there some slightly better looking way that we can iterate over this? Give me a second. Okay. What's going on with this? Okay, whatever. Um, right. So we have the data loader. And then let's take a look in this loop. Okay, okay. Right. And then we enumerate over data loader. So, um, because data loader does implement something that allows it to be an iterable, technically I should be able to just iterate over it directly. So for x in um, train data loader. Well, okay, it's not the iterable, right? The okay, hold up. I think I think maybe it's not in the class. Maybe because I'm trying to think of where exactly it's keeping track of some kind of index after next gets called, and I'm wondering if I'm wondering if the counter is being tracked in the iterable object or within the class itself. Because if I were to create a new iterable out of this class, it would reset. It would still give me, the new data. I don't know if I explained that well. But okay, print type X. Okay, so that's a list. Oh God, that is okay. Stop, stop, stop. That is gonna become a long list. We should not do that. I made this mistake before and it slowed everything down. Uh, so how do I iterate over this? Oh, you know what I could do? Because it's an iterable, maybe I could access it like this. It's not subscriptable. Okay, hold up. So this I'm focusing on something that is like, you know, out of what we are doing right now, like, but just let's go with this for now. Okay, Python iter. Okay, so we have yeah, let's also open up the built-in functions. Okay, Python provides two general purpose iterator objects. The first is a sequence iterator. No, the first, a sequence iterator, sequence supporting works with an arbitrary sequence supporting the getItem method. The second works with a callable object and a sentinel value calling the callable for each item in the sequence and ending the iteration when the sentinel value is returned. Okay, hold on. So in here, we have the iter and the next methods. Give it a second to load. All right, this returns an iterator object. The first argument is interpreted very differently depending on the presence of the second argument. Without a second argument, the object must be a collection object which supports the iterable protocol um, or the iter method. Okay, or it must support the sequence protocol, so the get item method, with integer arguments starting at 0. If it does not support either of these protocols, then type error is raised. If the second argument, sentinel, is given, then the object must be a callable object. The iterator created in this case will call object with no arguments for each call to its next method. If the value returned is equal to sentinel, then stop iteration will be raised. Otherwise, the value will be returned. Okay, I feel like maybe I should leave this question for Gemini. Just give me a second. Okay, right. So maybe I should leave this question for Gemini. This method is called when an iterator is required for a container. This method should return a new iterator object that can iterate over all the objects in the container. For mappings, it should iterate over the keys of the container. This is an object representing a stream of data. Repeated calls to the iterator's next method return successive items in the stream. When no more data is available, a stop iteration exception is raised instead. At this point, the iterator object is exhausted, and any further calls to the next method will just raise stop iteration again. Iterators are required to have an iter method that returns the iterator object itself. So every iterator is also iterable and may be used in most places where other iterables are accepted. One notable exception is code which attempts multiple iteration passes. A container object, such as a list, produces a fresh new iterator each time you pass it to the iterator function or use it in a for loop. Okay, so I think it's the iterator that's actually keeping track of like what gets returned. I feel like I need to implement an iterator to understand exactly where it's being tracked. Attempting this with an iterator will just return the same exhausted iterator object used in the previous iteration pass, making it appear like an empty container. Wait, let's try something here. Okay. How do we Oh God, everything is slowing down. Do I have way too many? Oh, yes. Okay, I have quite a few things open here. So let's close a bunch of these things. Okay, iterable. Wait, iterable and iterator, an object representing a stream of data. Okay, iterable, an object capable of returning its members one at a time. Examples of iterables include all sequence types and some non-sequence types and objects of any classes you define with an iter method or with a get item method that implements sequence semantics. Iterables can be used in a for loop and in many other places where a sequence is needed. Okay, so I'm guessing maybe get item is not implemented, which is why the subscripting thing didn't work. I'm guessing. I'm not sure. I could be wrong, but iter is implemented, which is why it worked fine. Which is why creating. Which is why creating um, an iterable out of that worked just fine. This method is called when an iterator is required for a container. This method should return a new iterator object that can iterate over all the objects in the container. For mappings, it should iterate over the keys. So, okay. Now, you know what? Okay, I'm not gonna like I feel like I'm just gonna waste too much time looking into this. I'll write this down for later, and later on I can look into it. So here we have this. We have the data loader. We're able to enumerate over it. And in here we have the batch, which represents the, in this case, 64 objects, and then X and Y, which is our, wait, X and Y represent our 64 objects. Batch is probably just an index. Yeah, batch is just an index. Because enumerate returns, let me just confirm that. So let's say we have, actually, okay, yeah, let's say we have this. Okay, maybe we shouldn't do numbers. Let's do that. And then for assuming this is our thing, so we have index and value in enumerate a, then we print out I. Okay, yeah. So the left side is the index and the right side is the value. Okay. Right. So here it is passing X. Hold up. How do I oh, you know what I could do? Train data loader. Okay, and then just so it doesn't run for too long, let's say if I equals 3 or if I equals 2, break. Um, right. So other than that, we can try printing out. Actually, okay, let's try printing this way. Okay, cool, great. Let's also get the length of this data loader. 938. That explains why the list was so long. There's, if I remember right, either 30,000 or 60,000 images. Well, images and corresponding labels. And if we divide that up into 64, so let's say 60,000 divided by 64. Yeah, that makes sense. Yep. So it's divided up into batches of 64. And so each batch is going to have a size of, so if I print out the length, That's weird. Wait, is it? Oh, it's I think it's because it's a tuple. Yeah, there it is. Okay. So, um, in this case, that's, yeah, hold on. That's why. So now if we are able to divide it up in this way, then yeah, cool. So, then we can do for, um, can I do this? X and X. Will that work? And then let's print out. Yeah, there it is. That is our very big list of image data. And this should be our, okay, so let's say features. Actually, no, I had to pause for a second because I was wondering about the names. So okay, we are iterating over this, and then each batch. So what we are iterating over is batches of data, right? Each batch has 64 items in it, but we are splitting this up into a tuple. We are unpacking it into a tuple, so we have access to the features and the labels separately, right? So if I do for y in actually, let's do for a in y, print a, then that's our labels, and they're all in the form of tensor scalars or tensor floats. Well, yeah, I mean, same thing, right? All right. Okay. So if we are over here, if we are enumerating over the batches, then what we are passing into this model is 64 items at once. Now, how does that work? How are we able to pass in 64 items? Well, okay, I know how we are able to pass in 64 items, but what I'm wondering is, wait, so hold up. I need to run some tests here. So model is our neural network, right? That is here. Model is our neural network. Model is expecting flattened data, right? But what we are passing in is a batch of data. It's important to keep that in mind because if I let's say I print out wait, x is a it's a tensor. Okay. So let's say I print out the shape of the tensor. So there's 64 of them. There's 64 of them. Uh, flatten starts at 1, doesn't it? Where's that flatten function? Yeah, this version of flatten starts at dim 1 by default. Uh Okay, so let's say we tried to flatten. Let's say we tried to flatten this at uh, dim 1. Okay, dude, at this point, I probably don't even need this. I probably just need, actually, I probably just need this just to get the next thing, right? Okay, so let's just, okay, train features, type, that's a tensor. Okay, all right. Now, if I flatten this, what are we looking at here? Hold up. A equals, you know what? Wait, okay, so we can do B equals this, but A can just be that. And then we print out A, and then we print out B. I'm trying to figure out if the flattening affected inside. I think it did. Yeah, I think it did. Yeah, it affected in, but like, did it get rid of that one? Because we started at dim 1. Yeah, it got rid of the one as well. That's interesting though. I never mentioned for it to. Yeah, that's kind of interesting. Why did that happen? Why did it get rid of the one? Let me check the. Are there any notes here? Okay, flattens a contiguous range of dims into a tensor. See torch.flatten. Flattens a zero dimensional tensor. What? Flattening. Flattening a zero dimensional tensor will return a one dimensional view. Okay, all right. Right, so this flattens the input by reshaping it into a one-dimensional tensor. If start dim or end dim are passed, only dimensions starting at start only dimensions starting with start dim and ending with end dim are flattened. Okay, what if I give it an end dim of 0? Start dim cannot come after end dim. Okay, so here's my thing, right? I was looking at this as dim 0 and then dim 1, dim 2 and dim 3. I don't think I'm wrong about that, right? So if we tell it to flatten from dim 1 if we tell it to start flattening from dim 1, my assumption is that it's going to go in this direction and like flatten everything there and make it like a contiguous one long like contiguous um, block of data. But then that doesn't explain why one has been gotten rid of here. Hold up, let's try something here. So let's create a tensor. Um, in here, let's create our first dimension. Okay, and in there we create another dimension. Okay, and then here we have 1, 2, 3, but then this should also further be divided. So we do 1, 2, 3, and then, right. Okay, so let's print out the shape of A. Oh, too many dimensions. All right. Now if we run this, oh, wrong. Let's just do b equals a dot flatten start dim equals 1. Oh, see, it gets rid of this dimension as well. I wonder if it's because it's 1. So, okay, hold up. We've got 3, which is 3, right? If I add an extra thing here, then 4 will be here. Okay, so this is one dimension. And then this thing, it holds these 4. So that's the second dimension, right? And then this 1. So this is, well, no, this 1 is holding these 4. So that's taken care of. Okay. That's our second dimension. And then this is what's holding our third dimension. So what if we did something like this? So now our dim 3, no, our dim 2 should say 2. It doesn't say 2. Oh, wait, I made a mistake. Yeah, I calculated wrong. Hold on. I made a mistake in terms of like counting the dimensions. So this is our dim 0, right? And then this gets collected into, oh, maybe it's because okay, so this is 1, right? So this is our dim 0, which has 3, and then our dim 1 is a collection of this, but I was counting this within this, right? Which I don't think I did. I don't think I was wrong to do that, because then that's where the 1 comes from, right? And then this is where the other 1. Oh, that makes sense. That makes sense. Yeah, that makes sense. Yeah, there we go. So now we're going to run flatten on this, and it still takes the entire thing. It takes this entire dimension. Right. So that's another thing I need to experiment with to understand exactly how flatten is working. Uh, but we can get back to this thing. So my doubt was this, right? We pass in x, and keeping this experiment aside, x's shape is probably going to be this, right? And if the neural network takes this, or well, if the first linear layer takes these many in features, then this is the asterisk part. So this is just how many ever dimensions are there. So it's just gonna it's gonna process all of that, and then it's gonna return the results for the entire batch at once, right? Meaning meaning what's being passed into the loss function here is not one value, it's 64 values. So it's the entire batch of data that's being passed in. So I think that's where my confusion is coming from, because I need to understand exactly how this data is being processed. Because here now it's calculating the loss for what, all 64 at once, I think. Yeah, I think it's calculating the loss for all 64 at once. And then we're also passing in, oh wait, we are passing in y, which is also 64 values, right? And then we do loss dot backward. How is this working? So it's operating on the entire batch at once. Yeah, it that makes sense, right? It's operating on the entire batch at once. I think so. It's it's processing the entire batch at once. It's then calculating the loss for each item in the batch, I'm assuming. And then loss dot backward is also being called for like every item in. No, hold up. If wait, yeah, what's that's not one value, right? Loss is not going to be one value. Loss is going to be an. I'm assuming it's going to be like multiple. Wait, I should. Yeah, hold on. I should try passing this into. Okay, so get rid of this. We can get rid of this. We can. Yeah. Okay. So um. So prediction equals model train features. All right. Cool. Then loss equals. Wait, where's our loss function? Oh, loss function is somewhere here. Where does this get called? Oh, loss function equals okay. All right. So let's do loss fn equals nn dot, what is it, cross underscore entropy? No, it's cross entropy loss. Cool. So here we have our loss. I forgot. Hold on. Hold on. Yeah, we call the loss function, and we pass in our prediction, and we also pass in our train labels. Right. Okay, yeah. So then first things first, I want to print out the type of loss. It's a tensor. Okay. Then let's print out the shape. Oh, by the way, quick thing. There's going to be an ad playing in like 30 seconds. So I'm going to start the ad break right now. And I'll see you guys in 30 seconds. I'll take a little hydration break as well. All right, welcome back. So this is kind of interesting. I don't think I've ever seen this kind of shape before. It's just empty. So this is a tensor with one value. Oh, that probably explains the shape. Wait, that's interesting. So hold up. If prediction, let's print out the shape of predict shape. No, let's print out the shape of prediction. So that's the shape that was that's the shape of the tensor that was passed in, right? But the loss value is still one, as in it's one value. That's interesting. For the entire batch, it has one value representing it. So I think this is where it's important for me to understand what is going on in cross entropy, so I can understand why it's passing out one value. Um, this criterion computes the cross entropy loss between input logits and target. It is useful when training a classification problem with C classes. It provides, if provided, the optional argument weight should be a 1D tensor, assigning weight to each of the classes. Okay, so now I have a couple of doubts that I need to like write down so I don't forget them. A couple of, well, not doubts, a couple of, well, yeah, I have doubts. Um, just, okay, create iter. That's it. Create iter out of custom class to understand it better and clear up the doubt about where exactly the quote unquote counter resides. All right. Next, I need to understand how exactly flatten works and why start dim equals 1 still seems to affect dim 2. And then the last one is how exactly, no, why is cross, or let's say, okay, CE, no, well, okay, cross entropy loss, taking in a batch of data, but giving out one value. Right. So these are things that I'm going to need to do research on in my free time. Okay, hold on just a minute. Sorry about that. Uh, Give me a second. Right. So, here's what we're gonna do. I'm gonna end the stream here, okay? But I'm gonna carry on doing this research that I'm doing. I need to get something to eat as well because I'm starving. We're gonna raid this person named Mostly Mochi. Um, let me. I don't know what they're doing. But we're gonna raid them. I hope they don't have like raid settings and stuff. Okay, cool. There's no limitations there. So we're gonna go raid this person. They're also doing a co-working and studying stream. I think they're studying something or doing assignments or something. But yeah, that's gonna be it for today's stream. Hopefully, I'm able to stream again tomorrow to do another talking stream, but I'm going to clear up these doubts that I have. And maybe, hopefully, by tomorrow, I mean, I'm saying that by tomorrow, I should have the training thing done. Like, I should have finished learning how to train the network, but uh, I don't know if that's going to happen. But yeah, that's going to be it for today's stream. Qtane, thanks for stopping by. Thanks for hanging out. Anyone else who might have been lurking in the chat, thanks for hanging out. Um, I hope I'm able to stream again tomorrow. But that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.